Okay, so guys, I'm gonna go ahead and start and tell you a few things. I I got all the homework, and my goal yesterday was to get it moved from Google Docs to Google Drive to blah blah blah, and finally into this app I've got that I was supposed to be able to grade it on electronically and send it right back to you. And even though it involves about 20 keystrokes, I think I succeeded. Did everybody get their homework back? Okay, you said, okay, all right, great.
Yes.
All right, good. That's a good thing. That'll make it easier for me. I do need one thing from you for that, though. I need you to send it to me in a particular form. Let me share my screen first, and then we'll talk about that. Let's see. Oh, come on. Yep. Okay, that's good. So that's just where we left off yesterday. I'll worry about that in a minute. We're waiting for everybody to come in. All right. When you send it to me, oh, I've lost my magic pen. There it is. When you send homework to me now, I already know it's Math 210 because it's going to a special folder because it's coming from you. What I just need you to put on it is your name, and if you're using the Genius app or any of those apps where you're scanning things in, it'll allow you to rename something. And what you do to rename that thing is just sort of tap what that number is that's the number of the document, and it'll say rename. So what I'm going to need is the name, and just put homework and basically whatever section it came from. So we'll say section. Actually, don't even do that. That's not what I wanted to do. Hang on. Just put the date on it. Just put the date on it. That'll help me sort it out. Okay. And that way, I mean, last night I had to go back and check these strings of numbers to see, whose homework it was. And I was in danger of sending the wrong homework back to the wrong person. Okay. It was not a perfect one-to-one match with the names and the documents. So, but that's going to be helpful to all of us, I think, particularly me, because I was trying to print things off. I was using enormous amounts of ink. I couldn't half read anything, but this works out great. So that ought to do. Does anybody got any questions before we get started today?
I have two more questions.
Okay.
And I just kind of need to, I don't think I'm doing this the right way.
Doing so what?
Over number 15 and 23.
Okay. Let me address the question you had yesterday first, Haley, and then I'll do that. Okay. So let me go back. There was if you remember, guys, Haley had a question on something where she was holding up the notebook for me to try to see it. And I didn't realize what she was asking me until I started grading the homework and sort of listened to what she said over again. So what you're looking at right now, guys, is the key to the homework from that you did yesterday. Everybody got pretty much all the points, so it turned out to be you might not need a key, but I'll put it online anyway. But one of the ones down here, the one that had infinite solutions, okay, that one right there. When you plugged in, Haley's question really was, well, it didn't look like you used the initial conditions, but I plugged in what they said the solution was, and it always came out true. Is that right? Is that an accurate depiction of what you were asking me, Haley?
Yes.
Okay. All right. So so when Haley plugged it, what Haley did was plug in the thing, and it came out to be 24 equal 24, whatever. It worked. Okay. And that was definitely showing it was a solution, and that C1 and C2 in some sense didn't matter. But what it didn't show is how C1 and C2 had to be related to make it a solution. So you did need to plug in those, initial values. I did not count off anybody for this thing because I didn't get to answer the question, and it would have helped you. So here in this one were the conditions. And what I plugged them in, when I plugged in this one, when I plugged in 0, and it was supposed to equal 3, it always equaled 3, okay? So it didn't matter what the C1 was, okay? When I plugged in 1 and got 0, I got C1 plus C2 plus 3. What that told me is that, yeah, I could find C1 and C2 that would make this thing true, but it was not a unique solution, because all that really had to happen is that C1 and C2 had to be related like that. If you think about it as a line, like x plus y equal minus 3, there are infinite points on it. So there are infinite things that can make that true, and they're related in that way. Okay, so that would tell you, for instance, if I were to write out the solution, I might write a C1 on it, and then where there was a C2, I might write out minus 3 minus C1 to tell me that I really only needed to know C1. That's kind of bad there. So a couple of people actually did that too. Is that clear? Does that make everything clear on that one? Haley, you see what I'm saying? I think.
Yeah, so you just plugged in the
Yeah, I plugged in the initial, this was a boundary value problem because these two things were different, okay? So I plugged those in, and I found out how C1 and C2 had to be related. And because I didn't get a unique solution here, that showed me there were infinite solutions, okay?
Okay.
All right, so let's go, let me go back and let's see what other questions you've got here, guys. I'm gonna go into what I'm gonna finish today, and then I'll try to work, I'll do the homework problems that you want to ask me now, if I can find it. All right, so everybody okay on when you send me homework, put your name on it. It can be just first name, guys, because it's a pain to rename those documents. So just put your first name on it, and then homework, and then the date. That'll work out fine. Okay. All right. So Haley, you had a question. Tell me what it was. Again. Unmute. You hear me, Haley?
Sorry, I answered, but I was on mute. Sorry.
Okay. Okay.
Just on number 15 and 23, I think I'm setting it up wrong.
Okay.
Or
so
like I was looking back at my notes and I wasn't sure how to set up the matrix.
Okay.
For 15, like what numbers to use?
Yeah, 15. This was the one where you had to determine whether a given set is linearly independent, right? And the set of functions that you had here was f1 equal x. So this is 15. 15. f1 equal x. f2 was x squared. 2 was x squared. And f3 was 4x minus 3x squared. Okay, is that the one you're looking at, Haley?
Yes.
Yeah, okay. So what we want to find out, guys, is whether it's the set's linearly independent. And what we found out right at the end of class on Wednesday, that you can test linear independence by using this thing called the Wronskian. And the Wronskian is just a determinant that takes the following form. The first thing it does is put the functions in the first row. So x squared, as usual, I got not enough room. Okay. And so this next one will be 4x minus 3x squared. All right. The next row, the derivatives go in. So that'll be 1, 2x, 4 minus 6x. Okay, so the first row is the function. The second row is the first derivative. The third row is the second derivative. So that's going to be 0, 2, and minus 6. Okay. Everybody with me? Now you ask about the setup. Is that, do you understand the setup, Haley? Everybody?
Where I need it, I can solve that from here because it's just a 3x3 matrix, correct?
Yeah. Let me make a comment on this though. Those of you again who had linear algebra kind of know this, and I said it, but I didn't use it very much. You can use any row or column with this process. And what we had been using was just the first row. If you look at the first row, there are no zeros in it. So if you took the Wronskian, it would be X times, and then you delete this row and this column, and then you do a subdeterminant. It turns out that you can use any row or column. So if I said, let's use this row, the advantage of that is that there's a zero there. So there's not going to be as much work to do. So for example, if I said, let's start this one out by using that row right there. So, and remember what the sign matrix looks like. It looks like this minus, this will be plus, minus, plus. So that's the third row. And that's because that's in the 3, 1 position. And if you add 3 plus 1, you get 4. And that would make this positive, although it doesn't matter with 0. But what happens here now is if I delete the row and column there, I don't really care what the determinant of the submatrix is. Why? It's going to get multiplied by 0. So in effect, you'll save yourself time if you pick a row or a column with zeros in it. After that, we'd put, that's in a negative position, so it would be let me get rid of I can't get rid of everything at one time. If I pick this this thing right here, what was that number? It was a 2. Okay. If I picked that thing right there, I would delete that row and that column, okay, and then use what was left for my subdeterminant. Point is, you'll do less work if you pick a row with zeros. Doesn't matter. You can check. So is everybody okay with that, with finding the Wronskian? All right, Haley, did you have another one? Because I thought I heard you say 2.
Yeah, 23. And again, it's just on the setup. I didn't just have another Wronskian or what. And I didn't know if it was about the operator notation that we covered last time.
No, you know something, last time I ran out of time and I had two more theorems to do. And so in 23, let me tell you what it asked, and then I'll just go into those 2 theorems that I didn't get to, because that'll answer the question on this, I think. 23 gives you a, it says a fundamental set of solutions. And you know what? I did not define a fundamental set, okay? So it's not the operator notation. It has to do with those theorems. So I'm going to go back and we're going to look at those 2 theorems. And then we'll go back and I'll answer that question. It'll be helpful to the rest of your homework, okay? Okay. Let's see. I keep thinking I can change my iPad by clicking on my computer. That didn't work. All right, so here's where we left off on Wednesday, guys. I had given you a Wronskian, a set of functions, and I asked you, are they linearly dependent or independent? And notice what we did here was put the functions in the first row. We put the derivatives down here. So derivative of 1 is 0, second derivative of 1 is 0. Derivative of x is 1, derivative of 1 is 0, and e to the x gets all the way down because it's its own derivative nicely. This, guys, is I use the first row here. So it'd be 1, and then delete and find the subdeterminant and so on and so forth. We looked at that. I asked you whether it was linearly independent or dependent. There was an e to the x there. E to the x is non-zero, so this thing is linearly independent. These things are independent. Okay. Now, this is a great example of where you could have used what I said a minute ago about picking a nice row. What would be the nicest row to pick here if you wanted to do as little as possible to do this Wronskian? What would be a nice row to pick?
Third row?
Yeah, third row, because in the third row, there's just a bunch of zeros there, which means I can jump right to here and say, well, 0 times any subdeterminant is going to be 0. 0 times any subdeterminant is going to be 0. The last one would be e to the x, and I delete that row and column, and I'd have 1 times 1 minus x times 0, which is 0, and I would just get e to the x. That's kind of the beauty of just picking something with a bunch of zeros in it. I don't have as much work to do. I have less room for error, let's say. Okay. Is everybody okay with that? All right. So what I didn't get to, and it was sort of like I told the whole joke and didn't get to the punchline on this thing, is a definition of something called a fundamental set of solutions. And that's what's in the problem that Haley just asked about. The definition says this. It says any set y1, y2 through yn of linearly independent solutions of a homogeneous linear nth order DE on I is said to be a fundamental set of solutions. Now, there are two things going on there. I want you to notice that the definition of fundamental set says that of an nth order has n things in it. So if it doesn't have n things in it, n solutions in it, it's not a fundamental set. It's got to have n. And there's a proof in the book about the existence of fundamental sets. But that set has n things in it. They're all solutions of the homogeneous system or homogeneous equation, and they're linearly independent. Okay. So that's what we mean by a fundamental set. So let me go back here. If in this one right here, we showed that these things were linearly independent. If I were looking at a third order, homogeneous equation there, that each one of these things satisfied, they were all solutions to that. There are 3 of them, it's third order, they all satisfy it, therefore it's a fundamental set. So when you're asked to find, if you're asked to show something's a fundamental set, the first thing you do is you say, well, what order is that equation? And if it's second order, you got to have 2. All right, so in that one that Haley asked me about, I think she asked me about 23, it's a second order equation, and they gave you 2 solutions, and you can check them out. And you want to check them out. You want to make sure they satisfy it. So make sure they're 2, make sure they're solutions, and then check to see if they're linearly independent. If they're linearly independent, they form a fundamental set. These things, solutions that form a fundamental set, are going to be kind of the building blocks of our solutions, of DEs. Okay, so that ought to answer the question of anything in 23 through 29. If you want to show something's a fundamental set, make sure you got the right number of things, make sure they satisfy your equation, and make sure that they're linearly independent. Okay. All right. So let's go back here.
So we're building a ROT-Scan again.
Say that again, Haley.
We're going to build the ROT-Scan again for 23.
Yes, exactly. You're just going to show they're linearly independent. Yeah, because elements of a fundamental set are by definition linearly independent. Okay. Most of those are pretty easy. I think only one of them has 3 things in it, but most of them are 2 by 2 matrices to show the linear independence. Okay. All right, now the next thing that's important to us, and this was basically what I just said, it says existence of a fundamental set. Existence of a fundamental set. There exists a fundamental set of solutions for a homogeneous linear nth order DE on the interval I. So right now we're looking at something that says we are going to find one of these things, and it's going to be a little while before we get to find out how to find them, but we're going to be building these solutions from this thing called a fundamental set. So there is a fundamental set when you're looking at a homogeneous linear nth order DE, and that fundamental set has n things in it, they're linearly independent, and every one of them satisfy the DE. Okay, so that's the homework that I'd taken you guys too long yesterday anyway, so I didn't even see what was under there. I'm glad I didn't see it because I would have been blabbing on for another 10 minutes, okay? So anyway, that's the homework that's on 128 that has to do with those two things, showing things are fundamental sets. So look at that again over the weekend at the end part of that. And there is some homework due in this section. I'll talk about that in a little bit by Monday at 5. And most of it is that just showing something's a fundamental set, okay? And doing the Wronskian. So that should be a fairly straightforward homework. Okay, that's it for that one. All right, let me get to another screen here, guys, so we can go on. All right, so this is what I call a final update on section 4.1.2. It's what I just said. If you've got a DE right here that is homogeneous, there is a fundamental set of solutions. And there are going to be n of them, and they're going to be linearly independent. N, and they're going to be linearly independent. So, for example, if I said, suppose e to the 3x and e to the minus 3x are functions y1 and y2 that we want to show they are a fundamental set. I didn't need that they, but anyway, I thought I did when I looked at it again. If I said y double prime minus 9y, let's look at the two solutions to begin with. So let's look at e to the x. If I look at e to the x here, y would be e to the x. Oh, it's e to the 3x, sorry. Y prime would be 3e to the 3x, 3e to the 3x. And then y double prime would be 9e to the 3x. Okay, it's nice to see e to the x's. They're easy to differentiate. So we want to show that's a solution. So here's what we would plug back into. It would be 9y double prime was 9, e to the 3x, and then minus 9y, y was e to the 3x. I get 0, clearly a solution to the homogeneous equation. Same thing, plug in e to the minus 3x, you'll get a solution, okay? The next thing I would do, they're both solutions, there are 2 of them, so I'm close to being a fundamental set. I need to make sure they're linearly independent. So when I do the Wronskian here, I put the functions in, e to the 3x, e to the minus 3x. I differentiate to get the second row. That'll be 9 e to the minus 3x. And I find the determinant of that. Okay. Okay, I got the derivatives right. I got 3e to the 3x and no, that's not right. Hang on. What's the derivative of that one, guys? I was thinking I was taking a second derivative. What's the derivative of that one right there? What should be that coefficient? Anybody? What should the coefficient be on? What's the derivative of e to the minus 3x? Somebody talk to me.
-3.
Yeah, -3. Thank you. Okay. So when I multiply these things out, remember it's easy when it's a 2 by 2 determinant. That'll be -3 e to the 0, because I'll add 3x and minus 3x, minus, if I multiply these two, it'll also be, it'll be 3 times e to the 0. I wind up with -6, non-zero, therefore linearly independent, okay? So those functions right there form a fundamental set, okay? Form a fundamental set. Okay, everybody okay with that? Anybody want to see the roll back and see the definitions again? We okay? All right. So, so here's my big theorem for homogeneous equations. There is something that we can write called a general solution of a homogeneous equation. And what it says here is that if I have n, let that be a fundamental set, and let them all be solutions of the nth order linear DE, then the general solution on the interval is this thing right here. Look at what it says. It's nothing but a linear combination of all the solutions put together. And we'll see in a minute why it's easy to see that that's going to be true. It has to do with the fact that derivatives can be found by adding and taking the C1, C2s, all the properties of derivatives we know. So if I go back, let me go back to where I was a minute ago, and look at what I just showed. We showed for this DE right here that these two things were formed a fundamental set. So the general solution for this one is going to look like this. It's going to look like y equal C1 times e to the 3x plus C2 times e to the minus 3x. In other words, it's a linear combination of those two solutions. Now, I will tell you that that's easy to see, guys, and I encourage you to check it out. If you look at, go up a little bit here. If you look at this thing right here, if you look at what the general solution is, must be Friday, first Friday of online. If you look at what the general solution is right here, okay, and go back and plug it into the DE, think about what's happening here, guys. Anytime you plug this in, it's a solution and it gives you 0. Anytime you plug this in, it's a solution and it gives you 0. So when you plug this thing in, if you were to split it up and separate it into pieces, I'd get a 0 out of that part and a 0 out of that part. And that means that that whole thing is this general solution. It will make the whole thing 0 too. So any linear combination of these fundamental set items it will be a solution, okay? And it's fairly easy to see, fairly easy to check.
Was that, so building that general solution, was that originally what we're doing, or did we just go back and do that?
That wasn't originally what I was doing in that problem, but that's with my new definition, okay?
Okay.
It says if you've got a fundamental set here, then the general solution is a linear combination of the things in the fundamental set. That's all it is. And I was showing you that one. I didn't ask that one in this question, but that's my new theorem. Okay. So let's see if I've got another example. Okay, so there it is. There's that theorem right there. And what I wrote down here is it says that this says really that any solution can be written as a linear combination of those elements in the fundamental set. So those are the fundamental set. Those are the linearly independent ones. And remember, if I added one more to it, it would be able to be written in terms of those. So n plus 1 would be too many for a fundamental set. Okay, you need exactly n of them that are linearly independent. And if you see another solution, somehow it is a solution of, it is a combination of the solutions in the fundamental set. Now, I've got an example for you, and I don't know if, it's one of my favorite examples in terms of showing what happens with fundamental sets. And it has to do with hyperbolic trig functions. And I always did hyperbolic trig functions in Calc 2. We've kind of gotten squeezed in Calc 2 lately because we cut our calculus courses down from 4 to 3. So a lot of times people don't teach that anymore. But I just want to show you something about something called a hyperbolic function. So look at this example right here. That thing right there is the one I was looking at a minute ago. We knew the fundamental set had e to the 3x and e to the minus 3x in it, which is, as I showed you just a minute ago, that means that any solution should be able to be written as a linear combination of those two, e to the 3x plus c2 e to the minus 3x. I'm going that right here. Okay, so there's a problem in the book that says show that this is a solution to that DE right there. Show that this thing right here satisfies that. Now, your first question's got to be, what in the heck is SINH? SINH is that thing called a hyperbolic sine, and it's called a hyperbolic sine. It looks like a hyperbolic trig function because a lot of times they behave like trig functions. For example, I'm going to tell you this, I'm not going to tell you why exactly, but the derivative of the hyperbolic sine is the hyperbolic cosine. That looks a lot like what happened in trig. This one is a little bit different. The derivative of a hyperbolic cosine is a hyperbolic sine. Why does that one look a little different from what we know about the trig functions, guys? What's different about that? If I left the h out and just was doing trig functions, how would this be different?
Sign would be negative.
Thank you. The sign would be negative, exactly. Allison's right. She's got, it looks the same. Well, it's not the case in hyperbolics. It's actually nice, which would be nice for Calc 1 students because they always forget which one a negative goes with, okay? But here's what I want to do. I want to show you that this thing really is a solution to that DE. So I'm going to take y prime, which if I looked at, there's the y right there. The derivative of hyperbolic sine is hyperbolic cosine times 3, because I've got to use the chain rule there. And then 3 times the 4 that was already there is going to be 12. The derivative of minus 5 e to the minus 3x is 15 e to the minus 3x. Now, I'm finding the derivatives, guys, so I can plug it in right here and show you that I get something that works. The second derivative of hyperbolic cosine is hyperbolic sine, all right? And then times the 3 onto this 12 will give me 36. And the derivative of that is minus 15 e to the minus 3x. So now what I'm gonna do is take those things and plug it into that DE. Okay, so that DE right there, and try to show that it's equal to 0. I want to know if that's a solution. Well, when I do that, when I look at y double prime up there, according to the definitions I gave you, minus 9y, which was the original function, I get 0. So that thing, that weirdness thing there is a hyperbolic sine. I mean, that thing with the hyperbolic sine in it is a solution. Now, here's the big idea. Because the things that were in the fundamental set were e to the minus 3x and e to the 3x, what that theorem says is you should be able to write this solution right here, all right, that solution right there in terms of e to the 3x and e to the minus 3x. Now, it turns out, guys, and here's the big kicker in this one, it turns out that the definition of hyperbolic sine just has e to the 3x's and e to the minus 3x's in it. If you look in your calculus book in chapter 8, in the section, it's like 8.4 or something like that, where they introduce these things, that's the definition they're going to give you. And the hyperbolic cosine is the same way. But notice, now you could multiply all that out and say, okay, 2 into 4 right here is 2. I multiply it out, I get this. That thing is a linear combination of the two things that were in the fundamental set there. E to the 3x, e to the minus 3x. So that fundamental set is going to be the basic building block of any solution that you're going to get. It's going to have the building blocks in it of any solution you're going to get to a homogeneous nth order DE. Okay, so I kind of stepped aside to do that one, but it's a great example. You don't know what it is, but I'm telling you, wow, it's defined to be exponentials. Okay.
For that one, are we proving that it's linear independent or that?
No, we're proving that, well, we'd already proved that e to the minus 3x and e to the 3x were linearly independent, right?
Yes.
So what I've said is that any solution you've got, whether it looks like that or not, somewhere under there is just a linear combination of those two. Everything can be written like that. And that's what I did here. What I did here was I told you, first of all, I verified that that was a solution, right? I verified that that was a solution right up here. So if what I've said is true, what happens is that it should be a combination of e to the 3x. Now I'm kind of pulled my trick out of the bag and I said, okay, guess what? The hyperbolic sign is just exponentials. And the hyperbolic sign of 3x just involves exponentials of e to the 3x and e to the minus 3x. When I look at that and put the definition in there, you can, and play it out, you can see it is a linear combination. See, there's a C1 e to the 3x plus C2 e to the minus 3x. It is a linear, that solution is a linear combination of those two elements of the fundamental set. Okay, let me show you another one. So everybody, that's a little out in left field because not all of you had hyperbolics, but it's a nice one to look at to say it doesn't look like that to me, but it turns out to be a linear combination of those things. Okay, so let's go, let's do one more. I've got consider y triple prime minus 6y prime plus 11y prime minus 6y equals 0. Notice, third order, linear, DE, homogeneous because it's equal to 0. All right. I want to show, if I wanted to show that this thing right here formed a fundamental set, first thing I ask myself is third order, are there 3 distinct functions there? Whoa, it's a good question. I'm going to have, that's an E, this is an e to the 2x, guys. That doesn't look very good, but it's an e to the 2x right there. Okay. So I've got e to the x, e to the 2x, and e to the 3x. 3 distinct functions. Do they satisfy the DE? Well, you can do that. All you're gonna need to do that is just take derivatives of these things and plug them in, okay? And you'll find out that every single one of them on its own is a solution. There are 3 of them, they're all solutions. The last thing I have to do to show it's a fundamental set is find the determinant that called the Wronskian. Okay, so that's what I'm finding right there. I'm finding the Wronskian. And when I do that, I'll let y'all check it out. I got 2 e to the 6x, and that's not 0. So they are linearly independent. Okay. Okay. So they form a fundamental set. There are 3 of them, third order, linearly independent. They satisfy the DE. They're a fundamental set. So the general solution looks like this. It's a linear combination of those 3 things, members of the fundamental set. Any solution we find to this DE is going to be some combination of those. It's going to be some combination of those. Now, you'll notice, guys, that I haven't told you anything about how I'm finding these things. That's what the rest of the chapter is about, okay? What we're learning now is the structure of how things have got to look. So they're saying, if these are solutions, well, you have no idea where those things came from. We're going to find out where they came from, and then we can form this general solution. Okay. Anybody questions? All right. Let's see what else I got here. Okay. I'm pretty much done with that section. The next thing I want to do is go to non-homogeneous things. All right, this is a little shorter section, but it will finish up this whole long section that's taken us about a week to do here. Here we go. Let's see. Non-homogeneous. Let's try this one. Okay, there we go. Okay, so non-homogeneous equations are exactly what we've been looking at, nth order linear DEs, but instead of being equal to 0, they're equal to some non-zero thing. In other words, the g of x, we were looking at this one a minute ago. Y double prime minus 9y equals 0, definitely a homogeneous thing because of this 0. If I look at it and it looks like this, it's non-homogeneous because that g of x right there is not 0. Okay. Now, a couple of times today I'm going to do, I just don't know why I remember this as Haley's favorite thing, because she said, I don't like those by inspection things. They're hard to see. Okay. So you got to make it easy to see is what I'm basically going to say. And you got to look for really simple solutions. So most of the time when you look for these things, they're going to be constant solutions. And you're going to kind of look at maybe the last thing. And constants won't matter if I take their derivatives, because their derivatives will always be 0. So can you tell me a function that would satisfy that based on what I just said, guys? Can you tell me a function that would satisfy that y equals something that would satisfy that linear DE? Hint, hint. Look at this and this. What would y need to be, guys, to get that? If it were a constant, what would it need to be? Tell me.
3.
Yeah, it would need to be 3. So that's how I do them by inspection. I was like, if it's not simple, you're not going to be able to see it. But it's hard to see when you don't know that, okay? So y equals 3 is definitely a solution there, guys. The first and second derivatives of that are 0, so that's going to be 0, and minus 9 times 3 is minus 27. Okay, so there's a solution. There's a solution to that non-homogeneous DE. Now, a couple of more sort of terminology things. Okay, any function yp that is free of arbitrary parameters. In other words, it doesn't have a c in it, it's just 3, that satisfies the non-homogeneous equation is said to be a particular solution of the equation. In other words, it's a solution to the non-homogeneous part. It's free of those C1s and C2s. Those C1s and C2s are going to be saved for the homogeneous part. So this thing right here, they call it YP because the P stands for particular. Okay, so YP is a particular solution. That's a particular solution to that non-homogeneous part. Okay. So if you were to plug it in, you should get an answer to that to the DE. Okay, let's go up a little further here. Something interesting here is what this theorem says. It says general solution of a non-homogeneous equation. What's that going to look like? Now, let me say one thing. Let me back up. I keep going back and forth here. Let me back up for a minute and tell you that there is something called the associated homogeneous equation. Y double prime minus 9y equals 0 is what I call the associated homogeneous part, the associated homogeneous equation for that nonlinear equation. In other words, if I didn't have that thing there, if I had a 0 there, that would be the associated homogeneous equation. That's important because I'm going to refer to that back down here again. General solution of a non-homogeneous equation. Let yp be any particular solution of the non-homogeneous equation on I, like I had minus 3 a minute ago. Let y1, y2, yn be a fundamental set for the associated homogeneous DE. That's the non-homogeneous DE with a 0 in the place of the right-hand side. So that's the associated homogeneous DE. Okay, on I. Then the general solution of the non-homogeneous system, the general solution of the non-homogeneous system looks like this. All right, let's tear that thing apart here. Notice that this first part right here, if you just look at those, that's just the linear combination of the fundamental set items. So for example, in the above problem that I did where the fundamental set was e to the 3x and e to the minus 3x, that part right there would be the solution to the associated homogeneous. That was the general solution there. And then what they're saying here is the the solution to the non-homogeneous will be those things plus the particular one that you found. All right, plus the particular one you found. And what was the, I think I got an error there. Let me back up a minute. What was the particular solution we found in, let me back up here. Got an error there. Oh, our particular solution in that one was 3. I do have an error. Okay. So this would be plus 3. Sorry. So plus the particular solution we found, plus 3. Okay. Now, let me show you why that makes sense. First of all, a little bit more notation. That part that's the solution to the associated homogeneous part is called YC. YC, where the C stands for complementary. I don't know where that term came from exactly, but that part is referring to the solution, the fundamental set linear combination that's the solution to the homogeneous part. YP is the one that's the solution to the particular one, to equal minus 27, the non-homogeneous one. Let me just sort of try to talk you through this. I've chosen to take out some of the proofs just because you can read them in the book. They're not hard to understand, but it takes up an enormous amount of time and energy to try to do that here. So if you were to take this whole thing right here, and plug it in to that DE we had, y double prime minus 9y equal minus 27. Each one of these pieces would cause that to be 0. That piece and that piece would cause it to be 0, so you get 0 plus 0, and then when you plug the 3 in, you're going to get the minus 27. So because those are solutions to the homogeneous part, they create zeros in the DE, and then what's left, that particular solution gives you the non-homogeneous piece on the right. We'll see a lot more of that. All right, let me give you another example.
Dr. Harold, I have
Sure.
I see like this makes sense, but like we were given y1 equals e to the 3x and y2 equals e to the negative. If we weren't that, how could we? You couldn't,
Haley. That's a good question. That's what I was saying a minute ago. You don't know how I'm finding these things. The rest of chapter 4 is going to tell me how to find these fundamental set solutions. Okay? It's we're laying the groundwork here. It'll look a lot easier. All the rest of it's going to give you some techniques for finding those. Okay? All right. So let's go to the next one here. So just to recap again, the general solution of a non-homogeneous equation always has the form YC plus YP. The YC is the solution to the homogeneous part, that linear combination of the items of the fundamental set. And the YP is the particular solution that makes it equal to the thing that's non-zero, to the thing that makes it the non-homogeneous part. So again, I'm going to give you an equation. You're not going to know where these things are coming from, but we're going to see what the structure has to look like. Okay. So that's important there, guys. So I'll give you a couple seconds here. General solution of a non-homogeneous equation always has this form: y equal the complementary solution, which is just the solution to the homogeneous part, plus the particular solution. And the complementary solution is that linear combination of the fundamental set items. Okay, let's look at an example. Here's a third order linear non-homogeneous DE. It's non-homogeneous because it's not equal to 0. It's third order, obviously, because it's got the highest order derivative is 3. So the associated homogeneous equation is this. Okay, so it's the whole thing, but it's equal to 0 instead of 3a. So that's the associated homogeneous equation. The fundamental set is this. And guys, that's e to the x, e to the 2x, and e to the 3x. You can show that I already sort of encouraged you earlier to show that's a fundamental set. It is. There are 3 of them. It's got to be a fundamental set. A linear combination of those items of the fundamental set is the solution to the homogeneous part. Now, you don't know how I got those. That's what Haley was asking. You have no idea how I got those. I'm just telling you those are solutions, and you can check them. And for right now, you should, because the book sometimes in the homework will try to throw something over on you and say, show this as a fundamental set. And you might find the Wronskian, and it might be non-zero, but you forgot to check they were actually solutions. If they're not solutions, they're not going to be part of the fundamental set. Okay, so you need to check their solutions and so forth. So if you were to take every one of these and plug them in there, you get 0. So that's why we start with that. Then you can show that a solution yp to the non-homogeneous equation, in other words, the one that's equal to 3x, you can show that that'll work. Notice it's free of any C1s or C2s. It's just a particular function. Where did I get that? You have no idea. Okay, you have no idea at this point. Okay, but that's what it is. So I'm going to write the general solution. The generals, and that's the fundamental set. I'll try to leave that at the top where you can see it. The general solution to this DE looks like this. It takes the linear combination of those members of the fundamental set. Notice C1, C2. That remember is the solution to the homogeneous part. If you plug that in to the homogeneous, that equation with a 0 instead of a whatever it was up there, 3x, then you would get that was definitely a solution. Homogeneous equation. I should call it the associated homogeneous equation. Okay? Equation. Okay. This is your YP. That's your YP right there. That's your particular solution. And here's what happens when you plug that in if you want to check it. If you plug this in right here, this whole thing, you find all its derivatives and you plug it into that equation right there, the one that's the non-homogeneous equation. You plug it into that. Okay. Then what's going to happen is all of these things are going to cause zeros. All of that's going to cause a 0. That's going to cause a 0. That's going to cause a 0. This is going to cause the 3x. Okay, and you will see that it will satisfy it. Because those are solutions to the homogeneous associated thing, they're going to everything you put in that has to do with that's all going to drop out, be 0. You put this in, this minus 11/12 minus 1/2, that's what's going to give you the 3x. That's going to give you the 3x. Okay. So that's the basic structure of a non-homogeneous nth order linear DE. I want you to also notice here that the coefficients are really nice on these things. They're just constants. That's going to be the first type we learn to solve because they're easy to solve. Okay. One more thing. Okay. There's something called the superposition principle for non-homogeneous equations. It's actually pretty easy. It's a mess to state, but it's pretty easy to see what's going on here. Let's suppose that these things right here are k particular solutions to an nth order to the non-homogeneous length order. I get tired. I've gotten tired of right now non-homogeneous linear DE. Okay, that's what that means. HLDE means homogeneous. Okay, so if you've got a bunch of particular solutions to these things where they're equal to different functions, In other words, if you look at this non-homogeneous linear DE, and on the right-hand side, you've got like a string of functions that it's equal to. I'll show you an example for this in a minute. If you've got that, then the particular solution looks like yp1, which is the particular solution associated with that function, plus yp2, which is the particular solution associated with that, and so on and so forth down here. Now, that's hard to understand from just looking at all that notation. So let me leave it up there for a minute, and I'm gonna let you write that, and then I'm gonna give you an example and show you what's going on here. So I'm gonna pull it back down a little bit. It's called the superposition principle, guys. It's 4.1.7, and I told, I guess it was Jessica the other day that that I am putting the numbers of the theorems down, and I don't think the numbers of the theorems changed in the new edition of the book. So those of you who have the 11th edition, if you want to just write this down and say fill it in, and then look at my example and read it back, that might be the easiest thing to do here. Okay. All right, so I'll leave it there for a minute. Let me show you what this means. Suppose we've got this thing right here is a particular solution to that DE. So there's your G of X, we'll call it G1 of X. Oops, I'm gonna call it anything, I can't get it written. Let's try again. So this is, say, G1 of X, and this is YP1. So if you put in, if you put in minus 4x squared for this thing, you'll come out with that. So YP1 is a particular solution. If you put in P1, that thing right there, into that DE, you'll get this, okay? And
What's the asterisk things mean?
I wanted that just means I wanted to refer to that later. So I'll come back up to it, okay? That's a good question. I had to think about it myself, but okay. So I've started with this example, guys. Here's the DE right here. And here's the G of X I want it to be equal to. And here's the particular solution that'll work. All right, now I want you to look at the next thing I've got here. YP2 equal e to the 2x is a particular solution to y double prime minus 3y prime plus 4y equal 2e to the 2x. Now, I want you to notice that the DE part of it, the part of it on the left here, is always the same DE. All right, it's always the same DE, but because this is a different G of X, this is a different G of X, we'll call it G2 of X, it's going to have a different particular solution. Okay, that's G2 of X. All right, one more. If I look at the next one, I've got the same DE, the same core DE on the left, but it's equal to a different G of X. So that's we'll call that G3 of X. And this is a particular solution when I use that G3. So to summarize, guys, I've got this core thing is the same, but I've set it equal to a different non-homogeneous piece. And it's going to have different solutions for each one of those non-homogeneous pieces. One of them was minus 4x squared for this one. For this one, it was e to the 2x. For this one, it was x e to the x. What we know, what the superposition principle says, is that if we have a DE, all right, that looks like this. I'm gonna block this right here. Let me move it a little bit. We have a DE that looks like this thing right here. Shoot, hang on. So this should be, the YP for the new one should be this. Notice what I've done there. If the solution looks like that and your G of X looks like this, okay? That was, those things right there, and that's where I had the asterisk here. Those things right there were the particular, well, actually I wanted to look at, sorry. I'm gonna look at one more. The thing I really wanna look at was right here. Look, there's a DE. Suppose you had that DE right there. Notice that this was that. This next one was that one. And this next one was that one. Okay. What the superposition principle says is a solution to that DE is going to be just a combination of the ones that were a solution to the individuals. That one went with that one. That one went with that one. And that one went with that one. Okay. So if you knew the solutions for these non-homogeneous things that were this, and that one, if you knew they were this, this, and this, then a solution to that whole thing right there is going to be this particular solution right here. In other words, you just combine the particular solutions for the ones that went with each G1. Okay.
So do we even, so our final answer is the original DE equal to the, all of the G of X.
What I'm saying is this. If that was the original DE, let me say it again. If that were the original DE right there, okay, the one, and notice it, and you knew solutions where all you had was this, and all you had was this, and all you had was that. They had the same core DE, but these were different G1s. That was a G1, that was a G2, that was a G3. Then the particular, here's what it's saying. The particular solution to this one, just as this was the combination of the G of X's, the particular solution is going to be a combination of the particular solutions for each one of them. So if I go back down here, the particular solutions were minus 4x squared, or minus 4x squared for this part. For this part right here, the 2x, this part right here, 2e to the x, it was e to the 2x. And for that last part right there, the solution was x. It was x e to the 2x. Okay, and maybe not e to the 2x, but e to the, it looks like e to the x. Okay. So if you got a string you've got a non-homogeneous thing, and you know that those things right there comprise a new non-homogeneous thing, and you know the solution of this one, and this one, then the combination of the three is going to be the solution of the combination of those. Okay. I'll show you one more example. Oh boy. Okay, we have some by inspection problems again. Okay. So look at this one. I'm going to change my color of pen here. So for some reason I'm going to change it back to, I'm going to change it to green, whatever. I don't know if I don't like that green. That's too light. I'm going to change it to that one. Okay. So this is non-homogeneous, guys. There's my function G1, okay? I'm asking you, what's a particular solution to that? Think easy. Think easy. Somebody tell me what a particular solution to that one would be. Find a constant. 5. There you go. 5. Okay. So so y equal 5 is a particular solution to that one. Pretty easy to see. All right. Let's look at another one. Maybe not quite so easy to see. Well, like I said, why don't we, in these simple cases, look at sort of that and find something whose derivatives might disappear and give me that? So what might you want y to be if I were just completely ignoring the derivatives to solve that? What would y be? We'll see if it works. What would I need y to be if I was picking something so simple that the derivatives started to disappear? What about that? Suppose that was 0. What's y going to be? Minus 2x. Everybody see that? Twice y equal minus 4x. I contend that yp in this one is, and I'll call this yp1. Notice these two d's are the same on the left and the right. yp2, look at minus 2x. Let's verify. It's easy. If you differentiate that thing, if you differentiate that thing twice, get it back, it'll be 0. And then plus 2 times that y will be minus 4x. Okay? So we've got two, I will call this my G2. The next question is this, and this is what the superposition principle is all about. What is the particular solution of 10? What is a particular solution of 10 minus 4x? Well, the particular solution of 10 minus 4x, notice 10 minus 4x is just these two functions right here. That was that and that. What the superposition function says is a new particular solution will just be a linear combination of, or just be those two together. Just put those two together. If you put a bunch of functions together to get a new DE, you can get a particular solution by putting their particular solutions together. That's it. Now we could check that by putting this in, and guess what? The 5 that we put in would generate this 10, and the minus 2x that we put in right there would generate this minus 4, and we'd have it. And you can check that. Okay, so there are my G1 and G2s. Here are my P1 and P2s here, and that's, combine those, or YP1 and YP2, and you'll have what you need. All of this lay in the groundwork for how are we going to do this lay. You have no idea where I got these things from. They use by inspection, because I know at this point students get tired of, where the heck did that come from? Well, if you can see it by inspection, at least you can see it where it came from. Okay. All right, couple of things here, guys. I want you to add 35A to the homework to hand in. That's one of these superposition problems, and I don't have the homework due until 5 o'clock on Monday, so I'll answer any other questions on this. Just to give you a one of these to work on. That 36 is one I actually did. There aren't many of these in the book. There are only 2, and I'm giving you 35A. So you can look at 35 and maybe 36 to practice on this. And I think some of those were in the original homework. But so that homework, that next homework that's due, is just fundamental set, linear independence with the Wronskian, and one of these non-homogeneous things. It should be a fairly straightforward homework. So I would, if you know, given the, I don't know if I look forward to weekends anymore. I just kind of sit around. But if you don't have anything to do when you're sitting around, go ahead and look at your homework. So if you have any questions for me Monday, we can talk about it. Okay. All right, I'm done for the day. I'm done for the week. This has been quite a week. My learning curve has been like, everybody in the news is talking about exponential growth of the coronavirus. I'm seeing an exponential growth in my my technological genius on teaching online. Okay, so what I'm hoping happens here, guys, just for in both cases, just so we can use some DE here. I don't want this exponential growth curve to go straight up. I don't want the coronavirus to go straight up. I don't want to be on that learning curve because I get tired. I want it to look like a logistics curve, okay? and I want the coronavirus to look like a logistics curve. Because what happens there is it doesn't go straight up. We don't overwhelm the hospitals, blah, blah, blah. My learning curve flattens out, and I don't go completely nuts by the end of the semester. Okay, so that's the kind of thing we're looking at. And I have pulled myself back from watching the news all the time because it really is because I know what exponential means, and I know what those curves look like, and so do you guys. So if you're a news hound, maybe you're not, take a break from it. I read something the other day that you shouldn't watch any more than 3 30-minute sets of news every day. And I was watching news from 7 till 11 every night. And I'm like, I don't need to see any more of this. So keep up the good work, and I will have a good weekend, and I'll talk to you on Monday. Any other final questions, anybody?
Just curious, do you know when our next test will be?
You know, we've done one section since we came back in a week.
I keep thinking it's more than one section. I know it's not though.
I know. And so what's going to happen next is when I start going into these other sections, we're going to be having some techniques. There will not be another test most likely until maybe the end of 2 weeks from now. Okay. I'll try to play it out this weekend and see if I can pick a good place. And I actually want to try to give, maybe put a little less on a test. This stuff I think will be old hand to you, but by the time we get some techniques to use, I'll try to play it out for you guys. Okay? That's an honest question. Answer that question. I have no idea. Okay?
Thank you.
Anybody else before I sign off? All right. Have a nice weekend. I'll see you Monday morning. Oh, don't forget your homework. It's due Monday at 5. All right.
Thank
see you later.
you.
Bye.